Next, we have discussed about the lightning arresters, rod gaps, and surge absorbers. Different types of protecting equipment we have discussed. All the protecting devices are, that's what we have discussed, they are non-shielding methods. Non-shielding methods means arc path can be existing between the line and the ground. Okay. So now for the direct lightning strokes or for the lightning protection against the lightning, we are using the shielding methods. Shielding methods means there is no arc formation between the line and the ground. So it will be completely shielding. So to discuss about this direct lightning strokes protection, first we will see what is the lightning phenomena. In a brief, I will give you what is this lightning phenomena, what is the intensity of the lightning, because I said lightning comes from the outside the atmosphere. Lightning over voltages, they comes from outside the atmosphere. That means outside the equipment, from the atmosphere, and not from the within the network. It is not switching over voltages. It doesn't depend upon the operating voltage. And whatever the voltage it may be, the lightning stroke will be same. If it is small voltage or large voltage, it doesn't depend upon the circuit conditions. That's what I said. So for this, we should know what is the intensity of the lightning. Let us see that. So lightning stroke, the voltage is 2 into 10 power 8 volts, 200 megavolts peak. The current is 4 into 10 power 4 amperes. The current in the lightning stroke. Duration is just 10 power 5 minus 5 seconds. Microseconds, 0.1 microseconds. The kilowatts is 8 into 10 power 9. The energy associated with this is 22 in terms of kilowatt hours. Energy is 22 kilowatt hours. You see, in 1 hour, 22 kilowatts. Such high energy is associated with that. So such a great intensive stroke it is. So for this, first let us see a small idea about this atmospheric conditions, because previously it is a wonder to mankind. They felt that it is an act of God. These things are there. They used to have about the lightning. But frankly, the first scientist in the 18th century has done the scientific research on the lightning, and we developed the proper phenomena. And thundercloud, as I said, you know, the height of the cloud above the base ground level is 500 to 30,000 feet. 1,000 to 5,000 feet, the charge centers will be there for the lightning. Actually, this is the height, but from 5,000 to 5,000 feet, actual charge centers will be there. 10 coulombs is the maximum charge in the clouds, which built up exponentially. And 10 megavolts to 100 megavolts is the maximum potential of the cloud. You see, such a high voltage. 250 kilowatt hour is the energy in the lightning stroke. So this is a very simple thing. A raindrop, if you take the diameter of the raindrop is 0.3 centimeter. Raindrops elongate and become unstable under the electrical field. So the field, in the field of 10 kilowatt per centimeter, in this field, this is the diameter. Raindrop velocity 800 centimeter per second. Free falling drops attains constant velocity with respect to air. And for size of 0.2 centimeters diameter size, this is the speed with which they fall. So air moves upwards with 800 centimeter per second. The air moves upwards with the same speed, no raindrop fall. That means if air's currents are flowing in the upward direction, we can expect the rainfall. So these are general knowledge point of view. Should have idea. More than 0.5 centimeters, the raindrop diameter is unstable and break up into small drops. Drop broken by air currents. Water particles gets positive charge. Air particles get negative charge. If it is an ice crystal strikes with the air crystals get negative charge. Ice crystals get negative charge. Air gets positive charge. No. So before going to discuss about the lightning stroke, one should know how the charge is separated in the cloud. So there are two theories, Williams theory and Simpson's theory. Simpson's theory based on the temperature difference. Let us see the Williams theory. You see, in the normal atmosphere, ions will be present. These ions, they surrounded with the dust and water particles. So this is the way normal atmospheric condition will be there. So if you see, this electric field intensity is 1 volt per centimeter above the surface of the air. For every centimeter, 1 volt. Once we are moving upward towards the cloud, then what happens? This electric field intensity will be reduced. Okay. So in 30,000 feet, it is 0.02 volts per centimeter. Near to the ground, there will be more electric field intensity. So let us take when the raindrop is falling like this, it is polarized because there are ions, etc. When the raindrop is falling, it is polarized. How it is polarized? It is a Williams theory. Upper part gets negative charge and lower part get positive charge. So this lower part positive charge attracts negative ions from the atmosphere and leaves the positive charge to the atmosphere. So whatever the positive charge left to the atmosphere by air currents, because air is moving upward, by air current it will move upward. Positive charge move upward, negative charge will settle in the bottom of the raindrop. Like this, when the raindrop falling in the cloud, the negative charged particles, negative charge of this raindrop, that will settle, which is a more weight, that will settle at the bottom of the cloud, and this upper part of the cloud is fully positive charge. This is the way the charge is separated in the cloud. So I think you understand the phenomena in this. So this is the charge separation. Now we can understand the bottom is negative charge, top is positive charge. Let us go ahead with the lightning phenomenon. Lightning, what is the lightning? A large spark accompanied by light, produced by abrupt, discontinuous discharge of electricity through air. It's a discharge through air from clouds under turbulent conditions of the atmosphere. Lightning is a discharge, simply it is a discharge. Discharge of cloud to ground. So if you take the cloud and the ground, it is a gigantic capacitor. Two plates of the capacitor. The upper part, lower part. You can see it is a two capacitor plates. And what is the dielectric medium between the capacitors? It is air. Let us see how the lightning occurs. It's a very interesting one. You see, the bottom part of the cloud is negatively charged, and then because of the, as I said, is a capacitor. When if you assume that it is a negatively charged, the earth is positively charged by induction. You can assume like this. So at 30 kilovolts per centimeter, that means maximum electrical field is 30 kilovolts per centimeter. But at 10 kilovolts per centimeter electrical field, the air surrounding this cloud will be ionized. So for the discharge, puncture in the air is required. That means puncture means ionization should take place. At this electrical field, air surrounding this cloud will be ionized. Then what happens? This negative charge, that means starts ionizing the air surrounding this cloud. Then these ions move like this. This is called pilot streamer, which has 100 amperes and which moves with 0.5 feet per microsecond. Cannot be detected by naked eye. It's just a spark. Come to the next stage. When this streamer moving, it ionizes the surrounding atmosphere. Then this is divided into step later. Like this, it is divided into steps. Each step is a 50-meter length. This is all by research they found. In microseconds, the step ladder will form like this. Once this step ladder reaches the ground, then what happens? We can expect this negative charge is reaching the earth, then it will be neutralized. So air surrounding ionized when the this ladder reaches the earth. This is called power return stroke. That means once it is ionized, already this path is there because earth is very gigantic, cloud is small, earth is very big. This negative charge is neutralized, and with the same path, these positive charges move upward because already a path is created. That means a puncture is already there. Through that path, these positive charges move upward. This is called power stroke, which is having 1000 amperes to like amperes, is 10% of the light speed, it will move like this. So when it is moving like this, what happens? Neutralization. That means all the negative charge in this separators, etc., they are neutralized with this positive charge. That neutralization will be visualized. Now you can see the flash, which can be observed by naked eye. What is the flash? Neutralization of the negative ions with positive ions. So that is visualized as a flash. So once the negative charge in the cloud, until the negative charge existing in the cloud, this neutralization takes place. We can see that repeated thunderclouds. Okay, these are neutralization. So again, like this, in the cloud, there are many pockets of the charged cells. So once this is completely neutralized, then again next pocket will take the same path, and the charges are slightly neutralized through this ionized path. Same path, in the same path, these will be ionized. Like this, you can observe the number of lightning strokes. So this is called dark ladder. That means the charged particle gets neutralized in dark ladder, which is 3% of the light velocity, will move more severe than a return stroke. Compared to this power return stroke, is more severe because nearby cells also getting neutralized. So like this thunder clouds you can observe. That means neutralization. So this is called lightning stroke. Energy in the return streamer lasts a few microseconds, which is called cold lightning stroke. Less than the dark ladder, as it lasts for few milliseconds. So hot lightning stroke. So we get some idea. Why can't you capture the energy in the lightning? Although the voltage associated with is more, the current is more, but it is lasting for few microseconds. Energy means time. You must have sufficient time to capture the energy. If you don't have the sufficient time, you cannot utilize the energy. It has power, but energy is less because time is less. But its effect on the equipment is more. Let us see what is that. So the lightning surge can be expressed by this wave. Already I said 1.2 by 50 microsecond wave. It takes 1.2 microseconds to reach its peak value. It takes 50 microseconds to fall 50% of this value. So we can express this wave like this. V is equal to V into 2 exponential waves, e power minus at minus e power minus bt, where a are constants, determine the shape of the magnitude of the step voltage. Where this is the T1, this is the T2. T1 is the time required to reach the peak value. T2 is the time required to reach 50% of this peak value. That's what I said. So where T1 is equal to 1.2 or 1 microsecond, and T2 is equal to 50 microsecond. This is the standard way of representation of the lightning wave. That means in less time, more voltage. So that is the representation of the lightning stroke. So in the lightning stroke, we can see there are two types of waves: direct lightning stroke and indirect lightning stroke. Direct lightning stroke. If you see, this is the cloud, directly it falls on this building, is a direct lightning stroke. A stroke occurs between the charged cloud and the earth. So there will be lightning arrestor, lightning conductor, which attracts the entire negative charge. We know the lightning rods we are keeping on the building, so that you have positive charge because that is earthed. This positive charge attracts the negative charge in the cloud, that will be properly grounded so that the building is safe. So if you take this is the indirect lightning stroke, that means because of induction, because there is a discharge from 1 to 2, because of these two there is a charge formation on the third cloud. So because of there is a B stroke will occur here. So these B strokes are due to sudden change in the charge conditions in the clouds. Okay. So these strokes do not attract this lightning rods, whatever you are keeping. Okay, this is the way direct stroke, indirect stroke you can observe. Now you got what is the direct lightning stroke and what is the indirect lightning stroke. Now let us see the discussion of the protection of the transmission line against direct lightning stroke. So you can observe here, as I said, a lightning stroke, the protection equipment is ground wire. Ground wires are nothing but the shielding methods. Okay, they are shielding methods. So direct lightning strokes are of concern of the lines of all voltage classes, as the voltage that may be set up is in most instances limited by flashover of the path to ground. And all voltage classes, these direct lightning strokes are concerned. Okay, you can see here two towers and there is a ground wire. This is the phase conductor and there is a direct lightning stroke here. And we are going to discuss about how the discharge takes place. Here you can see a tower. The top of the tower is the ground wire, and you can see the three phases. There is a insulator. There is a swing that will be given some swing. There are two ground wires here. These things you can have. There are H tower, T tower, different towers are there. We are going to discuss how the ground wire is used to protect the transmission lines against direct lightning strokes. Increasing the length of the insulator strings, these strings, merely permits higher voltage before flashovers occurs. Therefore, protective methods must be adopted to avoid flashover or breakdown of the insulators due to power voltage caused by lightning stroke. Some protective methods must be there. Okay, the most generally accepted and effective methods of protecting lines against direct strokes is by use of overhead ground wires. Overhead ground wires are used for protecting the transmission lines. This method of protection is known as shielding method. Why you say it is a shielding method? Which does not allow arc path to form between line conductor and the ground. I said there is no arc between line conductor and the ground. If it is a non-shielding method, you can observe across the insulator, you connecting a rod gap, there is a formation of the arc between the line and the ground. So that is danger. So in this lightning strokes, it is a non-shielding method. It does not allow the arc path. Let us see. The ground wires are the conductors. What are the ground wires? They are conductors running parallel to the main conductors. They are parallel to the main conductors. These ground wires will be there, supported on the same towers. Normally they are on the top. The top conductor is ground wire, which is properly connected to the ground, adequately grounded at every point on the tower and supported. It is connected to the ground. These ground conductors are made up of galvanized steel wires, ACSR conductors, you know this. They are provided to shield the lines against direct strokes. How they provide? By attracting the lightning stroke to themselves rather than allowing them to strike on the lines. So they will attract the stroke so that the stroke does not fall on the line. When the ground wire is struck by direct lightning stroke falls on this. Impedance through which the current is flows is very much reduced, and the correspondingly more current is required to cause flashover. So the main thing here you can see this is the tower. This is in the tower where Z0 is the surge impedance, natural impedance, and the current falls on this. It will be divided like this because it directly connected to the ground. This ground wire, this impedance is very less. You can write V is equal to I Z0 by 2. How the current is divided, let us discuss now. So overhead ground wire protects the lines by intercepting the direct strokes, keeping them off the conductors. So that means without affecting the lines, will protect by providing multiple parallel paths. You can see here, because of these two towers, we are getting two parallel paths, strokes, current to ground, multiple parallel paths to ground. The multiple paths for the stroke current results in the reduced voltage drop. Because of this multiple parallel paths, voltage drop is reduced. You can say V is equal to I Z0 by 2 because of the two parallel paths. When the ground wire is struck at the mid-span, because lightning can be either here, or somewhere else. If it is struck at the mid-span, then what happens? The current gets divided and flows towards the towers like this. As the tower current again gets divided between the tower and outgoing ground wire. So this current is divided. When the tower is struck by a direct stroke, there is only, if it is there is only one ground wire, there may be two ground wires or one ground wire. If it is having one ground wire, then what happens? Current gets divided to three paths. What are the three paths? One through the tower to the ground, and other two through the branches of the ground wires. The branches of the ground wires they will move. In addition to the above functions, And that means not only providing the parallel paths, reducing because of the low impedance, reducing the voltage. So that is the way the voltage will be reduced. What are the other functions of the ground wire? They reduce the voltages induced on the conductors from nearby strokes by increasing the capacitance between the conductors of the ground. By increasing the ground conductors ground capacitance, by increasing this because of these ground wires. So this voltage induced on the conductors will be reduced. So what are the main properties of these ground wires? They should they provide sufficient protection to the lines against direct strokes. What are the various things they have to satisfy? There should have adequate clearance between the line conductor and the ground or the tower structure. So line conductor and ground or the tower structure, they should not be clearance. That clearance will be given by this insulator swings. There should be adequate clearance between ground wire and line conductor. Some clearance must be there, especially at the mid span, in order to prevent flashover to the line conductors up to the protective voltage level used for the line design. The tower footing resistance, it is a very important point we are going to discuss now. It should be low as economically justifiable. Tower footing resistance, TFR, means the resistance at the foot of the tower. That plays very important role in this protection. We will discuss now. The ground wire should be placed at such a height above the conductors and so located that they should be well out on the towers and should not be exactly over on the conductor swinging under the ice loading. There should be some clearance and the position must be clear so that there should not be any swinging like this. So we are going to discuss some terminology associated with this protective ratio. Protective ratio means it is the ratio of induced voltage on the conductor with ground wire protection to the induced voltage on the conductor without ground wire protection. With ground wire, what is the induced voltage divided by without ground wire, what is the induced voltage? So this ratio is called protective ratio. The induced voltage under discussion is, what is the induced voltage? It is the voltage between phase conductor and ground. That means always we will take the phase voltage. What is the protective angle? You can observe here. That means the protective angle alpha is defined as, is afforded by the ground wire, defined as angle between vertical line through the ground wire. If you draw a vertical line here through the ground wire, okay, and the slanting line connecting the ground wire and the phase conductor to be protected. If you take this one, here there is a vertical line here, and there is a swing. You can observe that means insulator swing will be there like this. All insulator won't be like this. There will be some swing will be given. So because of this provide protection angle. So angle between the conductor and this vertical line drawn from the ground wire top, this angle is called protective angle. This alpha is normally in the range 20 to 45 degrees. So after the experience and all the repeated tests, this proper angle, protective angle, does not exceed 30 degrees. That means the swing must be like this. The conductor position with respect to the ground structure should be 30 degrees, so that a proper protection will be provided. You will see the protecting cone. Good shielding of the line conductors is obtained, and probability of the direct stroke to the conductor is reduced. But a protective angle of 45 degrees is satisfactory on hillside areas. That means if you go on the top of the earth, this angle will be increased. And if you go to the base of the ground, this angle should be reduced. Okay. So what is the protective zone? If you observe, just like a cone, okay, if you take a top, just like one triangle, you draw a cone, this is the protective zone. You can observe, protective zone is defined as the volume between the basic plane CBC, A, B, C, you can basic plane CBC, and the slanting plane AC extending from the ground wires to the plane. So if you take this line, just like a cone, if you see, this is the protective angle. Okay. What is this figure shows the cross section of the volume. AC cuts the base plane at C at a distance ky from the point B, vertically under the apex A. The ground wire is at a height AB is equal to Y above the baseline. You can see this one. The ratio KV by Y is called protective ratio. Okay. The protective zone is sometimes called as protective wedge as protective shed. So if you take this figure B, it represents a rod or mast with a height Y. Then it is said to be protective cone around the mast. The radius on the base of the line is equal to KY. So if you take a cone like this, the radius is KY and the protective ratio is KY by K. So what is the height of the ground wire? Where the ground wire should be kept? For the protection against direct strokes, the ground wire should be located at a height at least 10% greater than Y. What is this Y? Height of the ground wire. H is height of the conductor. So there is some formula like this, where X is the horizontal spacing between the conductor and ground wire. Conductor, ground wire, this is the horizontal spacing. And capital H is the height of the cloud. Y is the height of the ground wire. H is the height of the conductor. If you take, this is the formula corresponding to that, where it should be located. Though recommendations about the protective angle, protective ratio vary, experience has shown that double circuit lines will be completely shielded if two ground wires are used. Two ground wires are used, placed on one on each outermost conductor, height above the top of the conductor, equal to the vertical spacing between the conductors. Then it is a better shielding for high voltage. For high horizontally arranged single circuit lines, this is double circuit line. For single circuit, horizontally arranged single circuit lines, two overhead ground wires will give complete shielding. Overhead ground wires will give complete shielding if placed above the plane of the conductors at a height about 2/3 of the spacing between the conductors. Spacing between the conductors is 2/3. Between the conductors, if you take, the spacing should be 2/3. The distance between the two ground wires should be about equal to the spacing of the conductors. Between the conductors, what is the spacing? The same way, the two ground wires they are providing must have the same spacing. That will give a protection for the single circuit lines. For double circuit lines, should have two parallel ground wires. So coupling factor. These are the terminology associated with this. So what is the coupling factor? Is equal to square root of electrostatic coupling into electromagnetic coupling. So what is this electrostatic coupling? Since voltage of the same polarity as the ground wire voltage is induced on the conductors, entire ground wire or power top voltages does not appear across the line insulation. So that's why ratio of induced voltage on the conductor to the ground wire voltage is known as coupling factor. So induced voltage on the conductor to the ground wire voltage, that ratio is called coupling factor. Therefore, voltage across the line insulation is the ground wire voltage times the coupling factor. As I said, line voltage across the conductor divided by ground voltage. That means ground wire voltage is equal to coupling factor. Therefore, what is the voltage across the conductor? Coupling factor into voltage across the ground wire. Electromagnetic, electrostatic coupling factors are equal unless effective radius of the ground wire is increased by current. In which case, electrostatic coupling increases, electromagnetic coupling remains unaffected. So, unless the effects due to this corona is increased, this is increased. The coupling factor with effect of the corona considered is calculated like this. So, this is the coupling factor. Although it is a ratio, directly you can calculate from this multiplication of these two. The C is coupling factor, A is the distance from the conductor to ground, B is the distance from the conductor to image of the ground wire, and H is the height of the ground wire I have seen, R is the radius of the ground wire. The electromagnetic coupling factor is calculated using actual radius of the ground wire, and electrostatic coupling factor is calculated by the same equation using effective radius of the ground wire. Okay, it is with effective radius, it is with actual radius. These two coupling factors will be calculated. So next, very important point here we are going to discuss. We are going to finish with this reduction of the power putting resistance. TFR is the resistance at the foot of the tower. It plays very important role in reducing this lightning strokes effect. Effectiveness of the ground wire in controlling the lighting power voltage on a line at a reasonable values depends upon to great extent by lower tower footing resistance. What should be the general length? 10 to 20 ohms. It should be there, preferably closer to 10 ohms. For medium voltage lines, it can be less than 10 ohms. Foot of the tower, the resistance must be less, such that no, whenever the discharge current goes into the ground, there is no excess voltage developed between that for additional flash load. So sometimes some special means are employed to reduce the tower footing resistance. So special means are here: uh, ground rods, counterpoise, chemical treatment, all these things. Chemical treatment is required to reduce the tower footing resistance, but that is not possible because vast area is there. Everywhere you cannot do the chemical treatment. And we'll go for ground rods and counterpoise. Let us discuss about that. And the method to be used for reducing the tower footing is either by ground rods, counterpoise, chemical treatment. Either method is satisfactory. The proper low resistance is obtained. Deep rods may be driven on soil free from rocks. In the loose soil, you can use the ground rods, but that is not possible everywhere. There will be hill areas where you go for counterpoise. Let us discuss about that. The question is why we should have lower tower footing resistance. It is clear that whenever lightning strikes on a power line, current is injected to the power system. Current injected. Whenever the light strikes on the line, the voltage to which the system will be raised depends upon what impedance is the current encode. What is the impedance? That is important. Depends upon the impedance. Current into impedance equal to voltage. That voltage to which it is affected depends upon the impedance. If that impedance is reduced, then the voltage effect will be reduced. Say if the lightning stroke strikes a tower, potential of the tower will depend upon the impedance of the tower. So if it is high, if the impedance is high, what happens? Potential of the tower will also be high, which result flash over of the discs. As a result, line to ground fault, LG fault occurs. So the flashover will take place from the tower structure to the power conductor and therefore known as back flashover. So that's why the tower footing resistance must be less so that the voltage across that insulation will be less. So this is why tower footing resistance should be less. Reasons. So let us see the ground rods. What are the grounds are? Ground rods are used at the tower footing because I said the foot of the tower resistance must be low. How to maintain? Using ground rods. They are put into the ground surrounding the structure. They will put variation of the ground rod. You can see the distance, the deep. So here, how to reduce the resistance? Not by the size of the conductor, length of the conductor. That means how much length you are inserting into the ground. That is very important compared to the size of the conductor. That means thickness of the ground rods used is not important. The length is important. It is seen that more the length the ground rods is kept. Therefore, better is the reducing the resistance of the tower footing resistance. If you see 1.25 centimeters, if you say it is 2.45 centimeters, it is kept. Therefore, the resistance is reduced a lot. It is 1.25 centimeters. The resistance is a little higher compared to this line. So this is the way ground rods will reduce the tower footing resistance. But we cannot keep the ground rods everywhere. That means in the rocky area you cannot dig these rods. Come to the counterpoise. Counterpoise means it's a galvanized steel wire run in parallel or radial combination or two with respect to the overhead line. With respect to overhead line, in the foot of the tower, we'll keep some galvanized steel wires. So these are called counterpoise. So there are various configurations. What is the meaning of this? Here, if you see, these are the corners of the four legs of the tower. And the lightning stroke as incident on the tower, then what happens? It discharges to ground, through tower, and then through counterpoise. First tower is at four legs of the tower, then to the counterpoise. So if the surge impedance of the counterpoise, which is very important initially, once the surge has, this is the bottom of the tower I am talking. Once the surge has traveled over the counterpoise, then it is the leakage resistance of the counterpoise that is there. First surge impedance, next leakage impedance. While selecting suitable counterpoise, you can see this is the radial, this is a continuous, this is a radial and continuous lines, the galvanized steel lines that will be kept on the foot of the tower, so that whenever the surge travels, it will travel in the bottom of this ground, so that the tower footing resistance can be reduced. While selecting suitable counterpoise, it is necessary to see that the leakage resistance of the counterpoise should always be smaller than surge impedance. Leakage resistance is smaller than the surge impedance, so that the effective discharge can take place. So, mostly the last slide, the counterpoise wires are used extensively because of the difficulty encountered with the driving rods. I said ground rods, it is not possible to dig in the rocky soil. So in such case, this is the best method. They can be arranged either in radially, as I said, or continuous between tower to tower. We can keep, that means they are parallel to the ground lines, the bottom of this. Okay. So you can see here, this is the typical arrangements of the radial counterpoises. These are the typical arrangements of the tower to tower counterpoises. Continuous counterpoise wires, as you have seen in the previous slide, these are the continuous counterpoise, these are radial. Continuous counterpoise wires are more effective than non-continuous counterpoise wires. Current is drawn into the counterpoise from 1.5 to 2.5 kilometers away from the point of stroke. You see such a very effective. From the point of stroke, 1.5 kilometers, this stroke will be discharged and travel on the ground and fed into the stroke by means of counterpoise wire, the overhead counterpoise. The concentration of the current at any tower is thus reduced because this traveling. The reduced current at any tower causes reduced voltage drop. Then, and thus the tower potential is held to below very low value of the flash over voltage of the line insulators. So these are the measures to reduce the tower footing resistance. Okay, that is very important in over voltage protection. So that is the end of this discussion.